So we did one test and 2 months ago. So the first test is on the first 4 chapters. The second test will be on the next 4 chapters, chapter 5, chapter 6, 7, and 8. The last 3 chapters will be on the final. Every chapter will be on the final.
So we're not going to do this on the last 3 chapters.
The last 3 chapters, we kind of skip one test. So we don't have the test, I give it to you. I'll give you 2 tests. The final is from the ACS, from the department. So the next test, it will have the similar format. 30 questions, multiple choice. The way we study again is study the CRE first. The first test you did okay. So the class average, we have 19 students, 74%. And the second test may be a little difficult, or maybe easier depending on your previous study. So I just want to remind you, study like you have to study very, very good. Yeah, that's the usual way to study. So in this chapter, we study the gases, and I want to emphasize before we study like today's section by adding this slide, and I want to emphasize in this chapter we study gases, and we pretty much study like one model, and we call that ideal gases. Okay, you review the chapter. You read the book, it will tell you more details about ideal gas. Pretty much 2 major assumptions about ideal gas. So that's one, that means no forces between those gases. If you have a gas, helium gas, so you have a helium atom. So the ideal gas, assuming there is no attraction, no repulsion between those helium atoms. The second assumption is they take no volume. So they take no volume. So these are the 2 assumptions about in this chapter you can think about. You don't have to really like pay too much attention to that. Just know like we study those models. So then to study all those gas, so we use like 4 variables. We use 4 variables. There are 4 variables. 4 variables is pressure, volume, temperature, and N. So P is standing for pressure, and V is volume. We use 4 variables to study those gases. In most of the chapters, you're going to see like I give you some of those variables, you find out the other one. I might give you pressure, give you volume, give you temperature, something like that. You find out what is the N. Vice versa. Right? So to make the problem, solving the problem a little easier, we said we have 2 sets of 2 types of gas law. And all those gas law, maybe like 2 types or 3 types, we always deal with that 4 variable. 2 type, one, I call that individual loss, and the second one is the ideal gas law. Ideal gas law is what we're going to study today. It has a format PV equals N R and T. You can see that it's true what I said before. and you have 4 variables, you have 5 letters in this equation, but letter R is sort of the constant. So therefore, besides R, you have PV and NT. And this is the equation where I just tell you what is the relations. The law about relations. What are those relations about those variables? So if you summarize all those 4 variables, you have this equation. The other type, we have 2 types. The other type is individual. We have 3 of that. I mean, we studied 3 of that. And this has a format. This has a format like that. The second individuals is Charles law, which has, you can write either one on the top. And the last one we study is avogadros, and that has format like this. Alright, and you can see in this 3 examples of the individuals, all those individuals, they have a person's name in it. But that's historical reason, because those laws are very, very early, like 300 years ago, 400 years ago. So some of the scientists already find out those relations. So those relations, or those laws, they already find out a long time ago. So these 3 types, and in either one of that, you will see there's only 2 of those 4 variables. Let me put it on top again, there's 4 variables. 4 variables, P, V, N, and T. And in this first type, we call that individuals. In either one of these, there's only 2 of them. In borrows, for example, there's only P and V. There's no R and no N and T. In Charles, there's no P and N. In avogadros, there's no like T and N, T and P. So that's the individuals. The individuals only have 2 variables in it. Right. You also notice the notation. We write those 1 and 1, and then those 2 and 2. So therefore, altogether, you might have for this type. Let me draw a line in the middle. You might have I call that 2 sets of conditions. For example, you will have 2 pressure, and then you will have like maybe have 2 volume, 2 weight. The problem might not give you 2 volume and also give you 2 pressures, so otherwise you don't have a problem. But give you like 2 pressures and 1 volume and find the second volume. Or might give you 2 volume, 1 pressure, find the second pressure. So those, we call them sets. And how many sets? You have like 1 pressure and 1 volume and 1 temperature, 1 angle, 1 set. Right. For this, there's only 1 set. 1 set condition. Let's say example, 1 pressure and 1 volume and 1 temperature, and then want you to find what is N. Now also you have to see those sets is for like 1 type of gas. So today we also learn those gas, like you have gas A, and then you have like a helium gas and then oxygen gas together, right? So those sets, how many pressure you have for helium, how many pressure you have for oxygen. We talk about those. Okay? And obviously, if you have oxygen gas, you also have helium gas. For helium gas, you might have those pressure. And then for oxygen gas, you might have the pressure. Those are not the sort of two sets. Okay? You still have only one pressure for one gas. Alright, so use this one set or two sets, and you will be able to decide which equation you want to use. So if you find out you have two pressure, and it's about two volume, and you think about pressure and volume is given by the Boyle's law. If you have two temperature and two volume, you think about that will be the Charles law. It will give you two volume and two like different number of moles. So you think about use Avogadro's. If give you one pressure, one volume, one temperature, you want to find out what is the number of mole N. Use this one set, the ideal gas. Ideal gas right now only have this format, but today we are going to study how to use this, change that into many different ways. Two typical different ways is we can use this equation to a little randomly and find out a formula or equation for density. And then that equation for density will have that model mass. So therefore, we kind of have two equations. So both of that two equations will come from this equation. Then you will use a similar idea. So if I give you one temperature, one pressure, and you want to find out what is density, think about use this kind of equation. So once you know you are using this first type or the second type, you know like what equation you use. More importantly, is for the first set, for those individuals, and ideal gas is about the unit. It's about the units. So there are four variables. Let me put them again: pressure, temperature, volume, and N. And all those physical quantities have a unit. You have to be very precise what unit to use. Sometimes it really matters your result. Sometimes it doesn't matter of saving time. So in both of these two types of laws, the temperature is in Kelvin, temperature is in Kelvin. That's always. So in this chapter, whenever you see the temperature, if I give you the temperature already in Kelvin, that's good. Just use it right away. Otherwise, you know how to convert to the temperature. If I give you Fahrenheit, you convert into Celsius first, then you add on to 273. Alright. So then for the individuals, P, V, and N can be in any unit, but need to be consistent. Because in this first type, in the individuals, you will see, for example, PV. So you have that P1V1 equal to P2V2. Be consistent, which means if you use ATM for P1, and you will use ATM for P2. It doesn't matter you use ATM or millimeter mercury or PSI, as long as P1 and P2 have the same unit. Alright, similar for volume, and you can use gallon, you can use milliliter, you can use liter, as long as if you use gallon for V1, you use gallon for V2. Okay, but for this ideal gas law, we have the equation PV equals N, R, and T. You still have that four variable on the top. You still have pressure, temperature, volume, and N on the top. But in addition to that four, you have this R. So what is R? Yeah. R is sort of the gas law constant. No, that constant is just constant. Constant can have a different value too. So in this chapter, we use this number. We say R equals 0.08206. If you use this number, so this number you get from, you use ATM for the pressure. You use liter for the volume. So that tells you precisely, if you are going to use this PV equal to nRT, because you have R in it, and you have a number for R, if you want to use this 0.08206, you have to convert the pressure into ATM. Not at that. Then you can use ATM, you can use PSI, and you can use whatever unit as long P1 and P2 are the same. Now here, because you want to use this number, so therefore the pressure should be ATM. And this arrow tells you the volume. So volume you cannot use gallon, you cannot use milliliter, you have to convert it into liters. And as before, so the mole, the N should be in mole, not a millimole, not a kilomole, because mole can also have those prefix. So as I said before, the temperature always in Kelvin. Right? So that's about briefly like a summary. Again, I emphasize, I think that's probably good. And what I did for the first 4 chapters, whenever you see the mass gram, think about how you convert it into mole. Right? Use mole mass. In this chapter, you think about those gas law. Right? Think about which law is P1 times V1 equal to P2 times V2. How you use that. Okay? That's called Boyle's law. That's called the individuals. That means when you have 2 pressures and you think about those problems have 2 pressures, 2 volume, then you use the Boyle's law. Okay? Then you decide how to use it. How to use it, which means units. So you converting those pressures into ATM. You can convert, but that will save you some time if you don't convert. If you use that Boyle's law. Alright, any questions? Alright, so that's just a summary. Now let's go into details. Right? So we already studied that 3 individuals, that Boyle's law, Charles' law, and Avogadro's law. Okay? Now you can combine all the 3 laws together and produce one law called the ideal gas law. Okay? The ideal gas law that will look like this. The ideal gas law, it looks like, you already saw that. Pressure times volume equals N times R times T. Obviously, you can write that in different formats. If you have an equation, you can write that. Or you can write, for example, pressure equals N R T divided by the weight. Okay? So that is a different format, different variation. Alright, and so as you already know, the R is sort of the gas law constant, and so this R will depend on the units for the pressure, for the volume, and for the N. So therefore, if you want to use some numbers for the R, you will know like what units will you use. Okay, so again, in this chapter, most of the time use that number 0.08206. If you use that number, you make sure the pressure should be in ATM, and your volume should be in liter. Temperature, no matter what law you use, should be in Kelvin, and then the N should be in mole, not a millimole, not a kilomole. Again. So now, what is the usefulness of this ideal gas law? The usefulness of this ideal gas law is you can solve some problems if I give you 3 variables. So if I give you pressure, give you volume, and give you N, and you can find out what is the temperature. So give you any of those 3 variables, you can find out the fourth one. Okay? Another usefulness of this ideal gas law is if you don't want to memorize what is Boyle's law, what is Charles' law. I just said if, you probably don't, the better you just memorize that. Okay? But otherwise, you want to get the Boyle's law from this equation, you have to know what is the constant, what is not a constant. For the Boyle's law, you want to say the temperature and N is keep as a constant. So if you keep this N is a constant, and R is already constant, if temperature is also constant, so everything on the right side is constant, therefore you will recover what is so-called the Boyle's law. Alright, so that is about this ideal gas law. Now let's do some little practice how to use the ideal gas law. Let's see this one example is this. I tell you the ideal gas law 1. If you don't look at that title, you're presuming you have this problem starting from scratch, you want to solve the problem. So just as what I said in the first slide of today's lecture, just decide, is this individual or the ideal gas law? We have the two types of law, individual and ideal gas. How do you know which one to use? Depends on how many pressure you have for the same gas, how many volume you have for the same gas. And on this program, there's only one gas, nitrogen gas. Let's see how many pressure we have, how many temperature we have. How many pressure we have if we have pressure? There's only one pressure. How many volume we have? We don't have volume, we want to calculate volume. So therefore we have one volume. How many temperature we have? Only one temperature. How many N we have? Only one N. Okay, so this is the typical one set condition. Because everything together will specify in what condition your gas exists. Alright, so there's only one set condition. So therefore, one set condition, think about the ideal gas law that has a format PV equals nRT. Right, so when you think about this equation, immediately you will know this R I'm going to use 0.08206. I think that's a good habit, because otherwise you have to memorize different units for the pressure and for the volume. If you memorize this number, your pressure shall be atm, your volume shall be liter, your N shall be mole, and your temperature will be Kelvin. Alright, so therefore, you have this step by step. You are going to use this equation to find out whatever that you want to find out. And in this program, you want to find out volume. Two ways to do that. One way I think that probably you prefer is convert those numbers into the right unit, and then substitute them into this equation, and then solve that equation. The second way is, before you substitute, you find out an equation for the variable you want to find out, and then substitute. I think the book uses the second way. So I will try to use the first way. So let's say we want to use the first way, which means just convert everything into the right unit. Then we will just replace whatever here by their number and unit. So as we know, we have to convert, if not yet, the pressure from the atm. Well, that's good. So our pressure is already atm, so we don't have to convert. Alright? And then you read this equation, the second one is V. The V is the one you want to find out, so you don't have a number yet, so therefore you want to go to the next one. Alright? Next one will be this N. N shall be in mole. Do we know N in mole? N equals 0.845 mole, so that's good too, so already in the right unit. And then next one is R. R is a constant. You already decided to use this number, so therefore we have to convert those into those units. Right? So then next one, the temperature, so in Kelvin. You are given one temperature, that's in Kelvin, so that's good. So therefore you have that T equals 315 Kelvins. So everything is ready, you make a list. And then next, you just do the substitute. Substitute these few into the equations. Together with their units, you get 1.37 ADM. And volume you want to find out. And then this N is 0.845 more. And R is 0.08206. And at the beginning, you probably want to write those units and with the number. And then K is 315K. And we will put that in the parentheses too. Right? So this is one way to solve the equation, which means solve the problem, which means you just identify what is given and make sure they are in the right unit, then just simply substitute. Right? So then you check if you did the right or not. You can see this more here on the top, cancel out with more at the bottom. This Kelvin here at the bottom cancel out the Kelvin on the top. Understand? Right. So then the only next step is try to isolate or try to find out what is the weight. So as you started from like your previous class, so right now weight together with z. You want to get a weight by itself. What you do, you divide the number out. Understand? So next step, you will divide 1.37 ADM. On the left side, you do this, you should do the same on the right side. 1.37 ADM on the right side. So on the left side, this comes out. On the right side, you don't count out the number, but you see this guy, the ADM, and the ADM comes out. Right. So all the units come out except that liter. Now everything also went out on the left side except the weight. And then what do you want? You want to say weight by itself equals what? So therefore, right now on the left side there's only weight. And then what's left over on the right side, just some number multiply and divide. And then the units, there's only one unit with the liter. I think that is a little like easier way, because otherwise you can find out if I start with that equation PV equals N R and T, and we want to find out what is the weight. Okay, we will divide the pressure out. Okay, so you will take PV equals N R and T divided by P divided by P. So the P and the P come out. You will get a V equals nRT divided by P. And then you are starting from that equation. When you start from that equation, this equation is just a little different way to write that equation. It's still the ideal gas equation, which means one step. Therefore, you have to make sure convert the temperature in Kelvin, convert the pressure in ADM, then you put into this equation. Okay. So either you have this equation first, or you just starting from that equation, just put everything in, then divide, then you get that final equation V equals some number, so that doesn't matter. Right? Right? So now let's say like all the units goes out except the liter, so therefore you have 0.845 and times 0.08206, then times 315, and then you divide by 1.337. The only unit left over is the liter, so you put liter there at your unit. Right? It's very simple. I think this chapter like in that sense. So you will see those numbers just similar like that. All right. Any questions? No question? do a practice. Obviously, in this CRE, there is no title, so you have to like probably do a practice. You bring your mind, you like see like what equation you use. Okay, so let's first decide, shall we use Boyle's law, Charles' law, or the ideal gas law? Ideal gas.
Is the answer A?
The answer is A? Okay, good. So that's good. So that's good. You just starting from the ideal gas, right? So a little bit of like more work than the example, because you have the convert. I think that the volume is okay, the liter, right? The mole is okay. I mean the N is okay in mole, and what's not okay is what? The temperature show you in what unit? Right now it's in Celsius, but when you do the calculation, it must convert into Kelvins. Very good, yeah. Right. So the problem is, you want to find out the pressure, right? So now let's use the second way. Use what I did here, right? Instead of like substitute them in, and let's first find out. So let's first find an equation for P, okay? And from PV equals N, R, and T. Right? So this equation has P times V together on the left side. You want to find a number for pressure, or you want to find a number for volume, you have to have an equation for volume itself, or for pressure itself. Right? So what do? You find an equation for P is by itself if you have this equation on the top. Right? So right now this equation, this equation on the top or this equation here, you have the P and V together. So how can you isolate the P by itself? Huh? You divide the V out, right? Right. So let's do that. So we'll have that PV equals N, R, and T divided by V, divided by V. Yeah. So you can do that, and then you will have that P equals N, R, and T divided by V. And this is just a different way to write these two equations. These two equations are different, but so these two equations, and then both of these equations means ideal gas, so you are just convert those into the right units, like the temperature in Kelvin, and then you just put it into here. Right? So let's say we want to find a P. So the N should be in moles, 0.552 mole. Right? What number do you use for R? That. And what do you do about the temperature?
77.
So temperature right now it will give you like at what? Celsius. You can put it here to the conversion. Right? You don't have to make another like this and convert the temperature or something. Just make sure that whatever you want to convert. Now divided by what? Divided by volume, right? Volume should in what unit? Liters, that's good. So you have that liters. Right, so this is Kelvin. I think that's what you find out, right? You might start with this equation, substitute the volume here, then you divide it by 1. Now find out, I think at one step, your result looks like my result here. Right? At one step, you will see that. Because at the beginning, you might have this number on the left side together with a P, but once you divide that out, you have the same result. Alright, no question. Okay, so that's good. And so the second example is about this. Okay? Those are different examples about the ideal gas. So if you want to start from scratch, again you identify there's only one volume, one weight, and there's only one pressure, only one T for the same gas. There's no like second numbers. Okay? So therefore ideal gas law. Okay? And once you decide you're going to use this PV equal to nRT, okay? Right. So PV equal to nRT. So therefore you have to see like the pressure should be 18 M. Right? Right. You can do like one step again, or you can just convert them first. Right? So right now I have 24.3 PSI. How you convert the PSI into 18 M? Okay, so divide by 14.7. This is converting between the PSI and ATM. So I will put it here. And this actually has PSI in it, and then you will have the ATM on the top. So the PSI will come out, and the ATM will be on the top. Right. Do you know the volume? Yeah, so that's good. You have that amount of volume, right? What we want to find out is N. Therefore, we don't know N, right? Do we know what number we use for the R? That's kind of boring, right? Do you know what shall we do about the temperature?
Convert it to Kelvin.
273 plus 25. That's the first one.
298.
298. So that's it. So therefore, you will see that N will equals 24.3 divided by 14.7 times 3.25 divided by 0.08206 and then time, not really time. Okay. So when I make sure when you use the calculator, so these two numbers are at the bottom and I right here multiply, actually you know what to do, right? Right, you can either referring to your manual for the calculator, just make sure you know how to use it. All right, so that's this example. Okay, so what do we get? Anyone do the calculation? And then we get 24.3. 14.7 and 3.25. Right. So that's what I do a practice. What should we use? How many number we have for pressure? How many pressure we have for the gas? Right? If there's only one, use the ideal gas. Right? On the boil or on the Charles. Okay. What do we get? What do you get? What's the number? B? Okay. So how do you find out B? What equation do we use? The PV equal to nRT, right?
Yeah.
Okay. Make sure you just use right units. If you want to use that PV equal to nRT, you know R will be 0.08206. This problem becomes more and more difficult. I think the last year I have everything ready except the temperature, right? I mean everything in the right unit. So we decided we're going to use ideal gas. Now pressure probably in what? Yeah, so divide this one by probably ATM, right? So right, that is this 765 is millimeter mercury. So then you can multiply by the conversion fraction, right? For every one, you can do 1 ATM over 760. That is millimeter 760, right? Not 760, right? All right, who find out number? What do we find out? B. B? You find B? And let's see your practice. And that practice is close to 1, but it's not really 1 ATM, right? So you
Yeah,
just
it's
over.
going up.
Divide by 760. Like that. You have that by 1 ATM equals 760 millimeter mercury. So that's the equation, right? So if you are given 765 millimeter mercury, remember in this class we learned like whenever to the front is using the conversion fraction, which comes from the equations. Right? So right now you have the millimeter mercury, and you want to cancel this out. You see here you have this number 2, and you have this unit 2. Now here this unit together with 760. And if you want to convert, you have to use the equation into a fraction like this. Right? So this is how you convert the pressures. Very good. So at least you know like the equation you can use, right? Yeah, so then just some of the details. Everything. Okay, this is the calculation. Yes, yes. You go to like some store, like $70 something. Don't use like the phone. The phone is always sometimes just like you. All right. So that is how you get it. So you let's see you if you want you can just write the conversion like by themselves like this. Okay, so this is 70, okay? And this is 1 ATM. And this conversion fraction, I said in this class is so important. You know like how to use conversion fractions. Okay? So this comes out and give you how many ATM. Okay? And so you have 765 divided by 760. You pretty much get 1, but you want to be a little more precise. So 1.007 ATM. Okay? And the more is okay, so this is our pressure. So N 0.556 more is okay. Temperature in kelvins, so if you have 58 Celsius, make sure you're adding 273. 273 plus 58, and you get 331 kelvins. Right? And you said you want to use that this equation, right? You want to use that equation because in this equation you only have one N, right? In the question there's only one set. Right? So you can either do this and just find out an equation for weight. So I will say just divide the P out, right? So you get V equals N RT divided by P. Not everything is ready, right? You have the N in mole, and R you know what number you use, and temperature in Kelvin, and you should get a liter for volume. So let's continue. We have a 0.556 mole and 0.08206, and has like the ATM. and liter divided by mole divided by Kelvin. And then our temperature is 331 Kelvin. And that's the reason you will see why we use those units and we use that number, right? The pressure is 1.007 atm. Now let's see the calculation, right? So now everything here on this side, the more and the more comes out, right? That's very easy to see. Kelvin comes out. And then ATM comes out. Right. So you get this about 15.0 liters. All right. So I have this few like 3 examples of the ideal gas law, because if you have this equation. And in this equation, again, you have 4 variables. You have the pressure, you have the volume, you have the N, you have the temperature. If you give you any 3, you can find the 4th one. And obviously, that depends on how you use this R. You memorize R has that number. Right? This is about N. If you use ATM, if you use liter, if you use 0.08206, if you use Kelvin, the N you get should be in mole, not millimole. Okay? Then you probably ask me, how do you know you are going to use that PV equal to NRT, not the boilers, not the avogadros? Because you are only given one pressure for the same gas. You are only given one temperature for the same gas. Right? Yeah, so first decide, should you use the ideal gas, or the boilers, or the chowers?
Is it B?
B?
Yeah.
Maybe I did not do the calculations. Yeah, you want me to do B? Okay. Alright, so it's getting better. It's getting better. So right, so then let's do the next one, next section. So next section is about the standard temperature and pressure, called the STP. So STP is an abbreviation for standard. So this S comes from the standard, T from temperature, and P from pressure. So now what do we call the standard? What is the standard? Well, the standard can be anything. Then just the scientists just think about the standard temperature should be like 0 Celsius or 273 Kelvins. The pressure should be 1 atm. So even though sometimes we change their mind, so right now you see the standard pressure is not 1 atm, it's like 1 bar, but that's very close. So you just memorize from right now, you just have this one particular condition, not a whole condition, one particular temperature and pressure for the standard. Right? And so that we can simplify some of those calculations, or we can make some of those common numbers into a table, and you can use that. Right? So let's see if I give you a problem, and you want to find out, for example, here, which one has the greatest volume? You want to find out the volume. You want to find out the volume. So again, you just starting from the beginning, think about volume will probably have something to do with either of those individuals. Maybe with boilers, maybe with Charles, maybe with like the avogadros. Right? Because boilers has a P1, V1 equal to P2, V2. Charles has like V1 over T1. So what do we use? So we use boilers, Charles, or avogadros, or ideal? Okay. So yeah, this I did not tell you like directly or explain basically, what's the temperature?
Would it be A?
Yeah, that's like, that's the two good. Let's see, first decide what law should we use. What law we use?
Well, I mean, if you just use like regular theory.
Ideal, yeah, maybe how do you mean the ideal?
Regular theory in dentistry.
Well,
I
just
think not.
because it would have moles, non-moles.
Common sense, I use common sense.
Remember how do we decide we use ideal or Boyle's or Charles? You decide how many temperature we have, how many pressure we have. Right? So how many temperature we have? So what is the temperature we have? I don't tell you the number, but I tell you the STP. 273. Okay? 273 Kelvin. Okay? Right? And what's the pressure? How many pressure we have? There's only one pressure. That's for the standard pressure. What is that in 1 atm? Right? And what else do we know? What else do we know? From this whole set of problems, what else do we know? The mole. How do we know the mole? Remember what we said in this class? Whenever you see the gram, actually the very same as the mole, right? So all the answer has what? Has a gram. That means all those give you some mole, right? But you have different mole, but only one mole for one gas. Right? You have different grams, so therefore you have different mole, but you have different gas. You have the CO gas, you have the O2 gas, and N2 gas, and the H2 gas. Right? So for each gas, there's only one set. Right? So we know N. Right? For example, N, let's see, for example, for this guy, for H2. Right? How can you convert it from gram to mole? More or less. So you write 500 gram of H2. Right? So molar mass of H2 is very good, Maggie. How do you know it's 2.2 gram? Yeah, it's diatomic, so don't like simply take the number from the periodic table. H is 1.01 because it's H2, so therefore you just multiply 1.1 by 2, you get 2.02. And the unit should be gram per mole, right? And you already know how to use that. So right now you will put this 2.02 gram of H2, and then you will see 1 mole of H2 here. Right? And then this gram H2 cancel out, you get how much mole? Is that right? That was what's right?
I can see it.
So this is for one gas. And for this first answer, for answer A, for the H2 gas, will have this much more, not say how much more. That's why we say you don't have to do calculation, so you assume that as that. Okay? Now let me simplify, cancel out the gram, and you will just take 5.0 divided by 2.02. And this is how much more of H2. Not really you did not do the calculation, but you still like have those everything ready. Right? So just keep that, and we have so we have A. Now we probably give that a special name because this is about more of H2, so therefore we get a special notation. We said that is N subscript H2, which means more of H2. Right? So now we have that. Now let me clarify some of those informations. Alright, so that's yours don't need. You only need this number. I mean that's our equivalent, so you have this three number, right? So I can just think about should I use Boyle's or Avogadro's depending on how many numbers do you know for each variable. Do we know like two temperature? No, we only have one temperature. Do we know two pressure? No, we only have one pressure. Do we know like 2N? Well, kind of, but for one gas, there's only one N, we have different gas, right? Is that okay? Right? So what law should we use? What law should we use? The ideal, right? The ideal. Right? One set, one number for everything, right? You should use the ideal, right? So what you use is the PV equals N, R, and T. Right? What do you want to find out for this problem? What do you want to find out? What do you want to compare here? What do you want to compare is what do you want to find out? Volume, right? See volume have this equation? right? You can either do like what I did the first example, I just substitute everything in there, make sure the unit is right, and divide the p watt, and get a volume, right? Now let's use this format, right? So we see volume equals what? N times R times T divided by pressure, right? Make sure those units will be right, right? Now let's don't get the number, really get out, just use what we have right now. What is the N? Is 500 divided by 202. So this is our N. And R is 0.08206. Temperature is 273. So I skip those units. And what is the pressure? Right, now this is one number. We call that volume. This volume is for what gas? This volume is for which gas? For hydrogen gas. So now I will also make a substitution. We see the hydrogen gas volume with H2. So if you have this one, now think about what will the equation looks like for the volume of, let me just write one more number, for the volume of N2. Right? What will the equation looks like for the volume of N2? We compare those volumes, right? And we said those volume of those different gases at the same condition. Do all those gases have the same temperature? They all at what temperature? STP is 273. Do all those gases have the same pressure? What is the pressure? 1 What is the difference between those different gases? Number of moles, and that is because why they are different. Number of mass. They all have the same mass, right? They all have the 5 gram, right? Therefore, you have very quickly write an equation for the H2 and for the N2 will be 500 and divided by what? And think about that. And 9 times 0.08206 and 9 times 273 and then divided by what? 19. Okay? Now find out the number now. What should we divide here? If you want to find out the volume for the N2 gas. This number is what again?
28.
Do you agree? Okay. So here will be 28 upon 02. Okay. Where does this 28 upon 02 come from? Where does this 28 upon 02 come from? Molar mass, right? So you have that N2, okay? So we said that's the molar mass, what equals 2 times, right? We have 2N, and then 14.01, and that becomes 28.02. Alright, so that is my example, and now you can very similarly write an equation for the other gas, right? And so all the gases will have a similar equation, and they all have this phi is the same, this R is the same, temperature is the same, pressure is the same. The only difference is this number. For this H2 you have 202. For N2 you have 28.02, right? And for that O2 you will have what? For the next gas, what was the number here for O2? What is the number for O2 here? 32? Are you sure 32? What was the number for CO? 28 here, right? So all the numbers are the same, except you divide by either a small number or a large number, right? And I think that's why like Mike said it right? So the answer, right? So all the numbers are the same. If you divide by a small number, you will get a large number. Right. So now let's find out really like in the condition called the standard condition, standard temperature and pressure, what is the volume of one mole of ideal gas. That actually you just go back to this question, and so this question, I mean this equation here is written for 5 grams of N2. Right? If you want to find out what is the volume for 1 mole of ideal gas, right, at STP, and you just think about use that equation. So volume will equals N times R times T divided by pressure. And this equation is similar. You have that PV equals N, R, and T. Understand? Right? So I think it's pretty good. You have some math skills. You sometimes you get a bit rusty. You don't know like how to use it. Right? So if I have this equation, you can just divide the V out to get P, divide the P out to get V, or if you can divide the RT out to get A, and so on, right? So right now you have this equation for V. And you want to find out at STP, and then you just review the last CRE. At STP, that means you only have 1 temperature, 1 pressure, right? And 1 mole, because we want to calculate what is the volume of 1 mole, right? So therefore, I decided to use this equation, right? So now you substitute, right? We want to calculate 1 mole. So therefore, there is 1 mole. Now, how do you know I want to calculate 1 mole? Because this question, I mean, the volume of 1 mole of gas is this much. You want to verify that it's true, right? So you take N equal to 1, right? And R should be 0.02206. And temperature should be 273. How do I know temperature 273? Because it tells you you want to calculate that at STP. Right? So then what should be the pressure for our gas? 180N. Then you will ask, how do I know it's 180N? It will tell you the STP. Right? Alright. So you have those numbers and you put it in and you can calculate what is the volume of any ideal gas. No matter you have H2 gas or N2 gas or O2 gas or air or mixture. If you know you have 1 mole of gas and the condition is STP, just use this equation to find out what is the volume. And very easy calculation. You take 0.08206 times 273 divided by 1 times 1, you get 22.4 liters. Right? Now this kind of has a special name because this volume is for 1 mole. Very similar. You have this 28.02 gram is for 1 mole of N2. Now this volume is for 1 mole of gas. But gas is a little more tedious because you have to see what condition. Not only how much gram, you have to see like what is the temperature, what is the pressure, right? So that's about it. You have those this special name called the molar volume. Molar volume, that means you have 1 mole of gas at STP. The volume is 22.4 liters. So no matter they are gas, liquid, water, or what else, or molecules, or like eggs or marbles, if you have 1 mole, that is Avogadro number, right? So therefore, you will have that much of molecular of gas, or in general, maybe particles, maybe atoms, right? And the gas is immaterial because as I said, in this chapter we studied the ideal gas. So no matter what gas you have, if you have 1 mole of H2, you have this number. 1 mole of N2, you have this number. So it is important to recognize that 1 mole of different gas will have like what kind of mass, and then even though they have same what. You already know they have same what at let's say all the ideal gas at the same condition. They have the same what? Same volume. And then what the different, what the mass will be different because that depends on the molar mass. So even though you have that 22.4 liter of those ideal gas, you know that one more gas you have, right? So at STP, whenever you have 22.4 liters, you know you have one more of the ideal gas. Then inside that 22.4 liter of gas, what is the mass? Depends on what gas you have. And also like, that not depend on what gas you have is the number. If you know that you have that STP, the 22.4 liters, and you know you have one more, then you will have that Avogadro number something in there. Right? Now what other mass will be different? If you have mass, if you have 82, you will be a little lighter. If you have helium, a little heavier. If you have A2, even heavier, right? Alright, what is very important? So right now we know kind of like two information. We know the mass and we know the volume. Whenever you see these two numbers, or whenever you see these two quantities, mass and volume, make you think about what? Density. So all those, there's some connections. Okay? Now, let's see, like first, let's just emphasize that concept. Ideal gas, which means it's kind of assumption. So at one spectral condition, at so-called STP, just keep that in mind. Whenever you see STP, you know right away the temperature is 273, and your pressure is 1 atm. Right? And if I tell you you have one more of the gas, then the other thing you will know is their volume. So all those one more of those different gas is 22.4 liters. Now how many particles we have inside? I think this picture is proportional. They have the same number of particles. Even though we did not draw all those like Avogadro number out, but at least you have that principle. Right? So all have the same number of particles, but different ones. So these three balloons, they have the same volume, same temperature, same pressure. What is the difference between them? Mass. Now obviously, if you know the volume, and if you can calculate what are the mass, you can get the density right away. Take the mass divided by volume, and get the density. Right. So therefore, this section you will have a different way to find out the density. Okay? If you have that gas at STP, and you want to find out what is the density of your gas, depending on what kind of gas you have, and you want to find the density, just take the molar mass divided by 22.4 liters, and then that's it. Then probably you just also like wondering what unit you get for the density. Okay? Or because you are using that PV equal to nRT, those kind of conditions, so you are using gram for mass, and you use liter for the volume, and obviously you have more pressure is atm, and so therefore you get a gram per L. Alright, so that's simple. If you are given a problem, ask you what is the density of some of those gas, ideal gas at STP, you just find out what gas you have. If you have like oxygen gas, which means you have O2, right? So for O2, you will take like 32, right? Divided by 22.4, right? For O2. And if you want to calculate for some of those organic gas, for example, the cooking gas, methane, right? What is the density of methane at STP? Same idea, right? You will see what is the molar mass of CH4. Is about what? 12 is for carbon, for one carbon? Yeah, so you have 16.04, and then the gram, right? Then divided by what? 22.4 liters. Alright, so that is one possibility for those problems. And if you want to find out what is the density for those gas, and you just see what is the condition. Now that is only one spectral temperature, one spectral pressure. What about if you want to calculate the density at some other temperature and other pressures? Well, the result is this equation, and this equation at the bottom, D equals P is the pressure. This is the molar mass, and in unit gram per mole. And all the other variables the same as the PV equal to RT. Because we can see very quickly this equation you can get from this equation. Without any major change, just simply rearrange. Right. So therefore, this P should be ATM. This T should be in, as I said, should be in what unit? In kelvins. Then what number should we use for R? Yeah, 0.08206. Right. Well, just to make you alert, later on you don't be surprised. You can use some other number for R, especially in the later on this chapter or in the next chapter. Okay? So this R not only have this number. Okay? Now for those calculations in these few sections, if you talk about those volume, temperature, and N and pressures, you use this number. Right? So then the unit you get for this D will be, so this D you will get will be gram per L. Right? You can either memorize the equation, or memorize how you get the equation. So we start with PV equals N, R, and T. Density has, so we know density has this format, right? Mass over volume. Now in this equation, you pretty much has everything. I mean the first equation, you have the volume. You don't have the mass directly, right? But you have the N. So if you have the N, how can you get, if you have the mole, how can you get the mass? Multiply by the molar mass. Right? So let's call the molar mass in our molar mass. Understand? So this capital M is our molar mass. And now we know N times N. That'll give you what? That'll give you gram. Do you agree? If you have the mole, you times the molar mass, right? You get the gram. So those are the review. So that's what we did before in the first few chapters. Right? So if I have the, if we call that molar mass is the capital M, and we call how much more is that little n, so n times m gives us a gram. Agree? Kind of? Not very sure. Right. So now let's think about that is the truth, right? So if we take n times, we take the little n times capital M, we get a gram. Okay? Now we have this equation that what we learned in this chapter. Right? If you want to use this equation, what should we use for pressure? What should we use for volume? What should we use for temperature? You keep that in mind. Right? Right? So now what do we do? I will take this P, V, times N. Then N times M times R times T. Do you think that is okay? Or do you understand how we get this one from that one? Right? How we get this one from that one? Now, how we get this one from that one?
So if the grams, you have to multiply by the moles by the molar mass, you have to do it both sides.
Yeah, that's what we do. So we have that equation. Remember you have an equation, you can multiply the equation on both sides, you can divide on both sides, you can do whatever, you do the same. Right? So what we did from that equation, multiply m here. Even though I put an M here, but those don't matter where you put them, right? Right? Everybody understand now? That's strange. So now let's do something like that. Okay? I will just write that. Okay? I will write P times N equals N times N times R times T and divided by V. I will ask someone, how do I get this one from that one? How do I get this one from that one? Very good. You get this one from that one by multiply. I get this one from that one divide. Divide by what? Divide by 1. And you will say, why are you so confusing me? Sometimes you multiply, sometimes you divide. That's whatever you want to do, right? So you divide by the way, and you get this equation now. Right. Now let me just erase on those guys. Alright, so I will do something like this. P times M equals N times capital M divided by V times RT. What I did here? Anything really I did something like from that to get this? Not really, right? You can multiply those in the numerator, or you can just take the N times M divided by V, then multiply by the RT. It doesn't matter, right? Right. Did anyone has an insight? What do we call this? What do we call that? Why is that done?
Why is it?
Huh?
Because the top two cancel out to moles over liters.
Yeah. So remember what we said? The top two is little N times capital M is give you what? Gram, which is mass. And mass divided by weight is what? Density, okay? Right. So I will rewrite this one like this. P times capital M equals D times R and T. How did we get this one from this? Actually nothing, right? What you did, just rename it. So this one together we call what? D. Right, now you're almost there, right? Now you want to get the D by itself. Let me just say how you get this one from that. How you get this last equation from that. And what do you see? Similar? Very good. You divide RT out, right? You get this equation with the final result. Alright, so obviously all you did from get this equation from that, and that equation you know how to use that, the pressure from the ATM, volume from the liter, right? And so therefore you have this, you still have those conditions. Then the unit you get for D from the gram over L. So that's how you study. So that's you're good. So then you keep studying so like the. So now let's see some of those calculations, right? So you want to calculate density of nitrogen gas at 125 degrees Celsius and pressure of this much. Right? So you pretty much just think about what kind of equation you can use. I'm going to use boilers. Boilers don't have density, right? And you pretty much think about that ideal gas. The ideal gas finally becomes that D equals P times capital M divided by R and T. Right? This is actually just another way of writing the ideal gas equation. Right? So this is very similar as the ideal gas, which is PV equals N, R, and T. Because it's very similar, so therefore you keep that in mind. So your pressure from the ATM, your volume from the liter, your temperature from the Kelvin, your N from the mole. Right? So then let's just do the calculations. I think sometimes I prefer just do like those step by step. So probably we'll first convert them into like units. So we have this 125, then we have to add that, right? And that gives us what? Right. So then outline pressure is for 755 millimeter mercury. So as I emphasized before, you always have to use this. That's a very, very important technique in this chapter. Is about these conversion fractions. Right? So if you know that the equivalent between ATM and MMHG, if you have that much MMHG, you want to get the ATM, and you divide the MMHG out. Right. So we get 755 divided by 760, and you get 0.993 ATM. Right. See the equation, the problem becomes like kind of like you have the density equal to this number, right? What else? What you need is the pressure, and what is the capital M standing for? Molar mass. And do we have the molar mass, or can we calculate the molar mass? What was the molar mass? What was the capital M? It depends on what gas we have, right? So now look at the question, what gas do we have? Nitrogen gas, hydrogen gas, oxygen gas, those are sort of the so I like what Maggie at the beginning said, diatomic element gas. Okay? So we have 7 of that. Okay? So remind you H2 and N2O2 F2 Cl. Not all gas. I mean some of the gas. I just realized some not gas. So just diatomic elements. Okay? Diatomic elements. Right? So you have 7 of those diatomic elements. H2, N2, O2, F2, N2, and Cl2. Right? I think what is important is when I said something like nitrogen gas, oxygen gas, you don't simply use N. You know you have N2. Right? So therefore you have 2 times 14.01 equals 28.02. What the unit? Is gram per mole. Well, what else do we need? We need to find out the D. And in this equation, we have pressure, we have capital M. What else do we need? R. Right? R. What R do we use?
1082.
Right? Why we use this R? Why we use this R? Is because this equation you get is from this equation. Right? So in this equation, and so if you use pressure ATM, you already convert it into ATM. If you use Kelvin for temperature, and if you use so that's about it, right? You want to use mole for N. All right. So then next is very simple. Just plug those numbers in. Alright, so we want to calculate the density, so we have D equals pressure, you want to see is 0.993, and 28.02 is the capital M, R is 0.08206, and temperature is 398. So all those numbers is easy to identify, but sometimes just also very easy to forget the unit. When you do more and more practice, and you probably make more and more mistakes, so sometimes you will learn from those mistakes. You will be able to memorize on the test. Okay. I think the other is numbers. You just put those numbers in, you get this final result. 0.852 gram per L. Alright, so now the comparison problem. So let's do this CRE. We have 4 most common gas in the air, N2O2, argon, CO2. And 2 of that is diatomic element. So read the question carefully, see what you have for each one gas. How many temperature you have for one gas, how many pressure you have for one gas. If you decide you're going to use one equation, and from that equation you can get the equation of density. Yeah, this chapter has a lot of equations. They are different than like chapter 1, chapter 2, 3, 4. He uses like 1 liter equals 1,000 milliliters. And this chapter you have those different laws, right? So first decide what equation to use. Do you have a formula or equation for density you want to calculate?
With E, the answer?
Yeah, you have the last equation we said is similar as this, right? So first decide. You can use that equation. What equation you can use? D equals what? D equals that, right? In general, D equals P times capital M divided by R and divided by T, right? Okay, so what's the answer? E? I don't think so. Is it E?
E.
E?
E.
How you get E?
Because it's the highest amount of.
Well, because if you want to have the highest density, so let's see what equation we use. The equation called what? D equals what? Pressure times what? Capital M divided by R times T. Right? So then you can see for all those different gas, what the pressure they have. They all have the same pressure, right? For all those gas, do they have different R? Same R. Do they have the same temperature? All the same temperature, right? Yeah, so kind of easy question, right? But then if you want to calculate, and you just need to convert the pressure into ADM, right? If you want to calculate, but in this example you don't even have a number to calculate, right? To make sure this pressure is what? ADM, and the temperature is what? Kelvin. The R, the number we're going to use is 0.08206. So even though you don't have a number in this program, so you know this all are the same. P is the same, R is the same, time is the same. So this equation tells you density, so D, right, is directly proportional to capital M, right? Directly proportional, right? That means if the capital M is larger, the density will what? Will be larger. So now you make sense, right? So which of those gas have a larger molar mass? It's kind of easy. You already know how to find the molar mass for N2, which is how much? 28 grams per mole. What is the molar mass of O2? So that is 32. That also you take 2 times 16. What is the molar mass of argon? About 40, right? What is the molar mass of CO2? How do you find the molar mass of CO2? Right? 44. Right? 44 equals 12 come from 1 carbon, right? And then 2 times what? 16. So that's 44, right? All right. So that's And you can see the molar mass, the largest molar mass is CO2. Right? Right, any questions? I think I'll do the reverse, that's the reverse. Right? You are given density, and you want to calculate the molar mass. Okay, what equation we use? What equation you use to find the molar mass for this problem? If you know the density, what equation do we use?
Is it D?
PM over RT. Yeah. This is D. This is D.
That's what I got.
Is D. Okay, did you also use that D equals P times M over RT?
Yeah.
Do you agree? Do? You can do that. You can do that. No, this is not the standard for this one. For this one, not the standard. You don't have a standard. You can assume that as a standard. That means they're also the same. You can do that. But for this one, actually they did not tell you the standard. But you can. You can just use the standard that they're all the same, right?
So I can try to control this simple equation and that one is to,
That will have the same result. But this kind of like it's okay. It's okay. It's okay. But you don't have to use like really those numbers. You don't really use numbers because if you use that means you only compare one spectral same condition. Yeah, that is the same. You can same that means you can add all them as STP. That's all they are the same.
so this is okay to use true for that.
Yeah, for this problem is okay. But in general,
So this is better?
that is better because that is more general. And you use that in only one special condition. That condition is STP. Yeah, it just tells you they are the same. It just tells you they are the same. STP, that means if we are all in STP, they are all the same. They can be the same as other temperature, other pressure. Yeah. You use one particular STP to get a more general result. That's okay. But you can get more general from more general.
But this is still regular to do.
Yeah, but I said it's kind of limited because you have to use some of those logical thinking. You see, I get that from one particular example. But in general, you can have any temperature, any pressure as long as the same. What you get is the temperature 0 Celsius, pressure 1 atm. And obviously, you can have the temperature is 700 centimeters. And if they are all the same, that. All right. So the equation, I think most of you get that right. Any questions? All right. So if you start with D equals P times M divided by R and T. Right? And so therefore the capital M will equal P times RT divided by T. Do you agree? How do I get this one from that one? That equation you memorize, right? That equation you memorize. How do I get this equation for capital M from the first one you memorize? Huh? You multiply by 1. You multiply the RT, then you do 1. Then divide by the pressure. Very good. So you see you have the math skills. Just kind of review. I know like the feeling when I study those chemistry class. Suddenly I see some of those math skills. Kind of, oh, these are the math I done before. Right. And just make sure if you want to use this equation, this will be in Kelvin. So therefore, we first convert 23 plus 273, that becomes 296. And your pressure is ATM, that's good, 0.789 ATM. Your D should be in something gram per. So that is kind of new. So if you want to use that equation, and remember what we did in the last example, if we use ATM and Kelvin and more, we will get this unit for density. So therefore, you should use density in this unit, then you will get those molar mass in gram per mole. Okay? So if I give you some problem, if I give you the density which is not in this unit, maybe gram per ml, you have to convert this into the gram per L. But that's usually probably I will not do that, but you know you have to have that unit. Right? You are right. So the answer is D. Right? The answer is D. Right? So then again, what about if you want to find out the molar mass at some other temperature and pressure and volume? Not like those, not those conditions I give you, like give you the densities. Right? So then you can either use what you learned, like in the what we learned in the last CRE, right? And that you can still use that equation. Okay? So if I give you, in the last equation, if I turn back to the last CRE, okay? So in those kind of problems, you want to find the molar mass. What I give to you is D. Right? So that directly gives you, give you the D, and I give you the pressure, and I give you the temperature. You put it into this equation, you calculate what is the molar mass. Now, what about if I give you some condition that you don't have the density right away? I mean, you don't have the density really give to you. Right? But I will give you the mass, and I will give you the volume. You can still use that equation like that. That equation, the capital M equals what we said, the D times the RT divided by P. You can still use that equation. Right? Do you agree? And if you want to still use this equation, that means you have to know what is the D. Now this problem tells you want to find the molar mass if given mass and temperature, pressure, and volume. So are we given the D directly? No. Are we given the temperature? Yes. Okay. Are we given the pressure? Yes. Okay. So therefore, if I give you the mass and the volume, what you can do, if you want to use this equation, you have to find out the density first. Now how can you find the density first from those information here? You simply take the mass divided by volume, but make sure your mass should be in what unit and your volume should be in what unit. Yeah, very good. Your mass should be in gram and your volume should be liter. Right? So that's depend on what you do. If you memorize that equation, if I give you density in the last CRE, you just use this equation right away. If I give you the mass, and if I give you the, so we'll probably take a break after we study this slide, right? Right? So if I give you the mass, and did not give you the density directly, I give you the mass, and I give you the volume and the pressure and temperature, what you can do, you can prepare those numbers first, just divide the mass in gram divided by the volume in liters, get the D, and you know how to use R, you know how to use T, you know how to use the P. Right, well, that's another way to find out the molar mass. Right, so that's the first thing about molar mass. What is the unit of molar mass? Gram per mole. Which means, if you think about what is the unit for density, density is usually what unit? Gram per liter or gram per ml, right? So from those units, you can find out another way to find out the molar mass. Because molar mass is a gram per mole. So therefore, if you know how much mole do you have, moles divided by what? Well, more sure it's not there. Right. So if you know the grams and you think about how can you find out the molar mass? Okay, so like that. If you know like what is the total gram of your xanthrose you have, okay? And you also figure out how much total moles of the xanthrose you have, you just simply take the gram divided by moles and get the gram per mole. Right? So this will be our that will be our starting point for this. Right. Now let's go back to analyze our problem. Do we have the gram? Probably not directly, but at least we are given what? We are given the mass, so therefore we can find out what is the gram. Right? If I give the kilogram, you just convert it into grams. And if you want to use this equation to find the molar mass, so the gram or the mass will give to you, so that kind of simple conversion, you can convert in kilogram into grams, converting like a pound into grams, ounce into grams. Right? So probably when I see that, you concentrate on that. How can you find out the mole? How can you find out mole for the gas? Depending on what it gives to you. Right? Now what else it gives to you besides the mass? Besides the mass, what else it gives to you? See, what is this condition gives to you here? Given what? Temperature, what else it gives to you? Pressure and volume. Now how, if I give you one temperature, one pressure, and one volume for the gas, what do you use to find out the mole? Ideal gas law. Right? Right. So this is not a really problem, because I just tell you conceptually, you want to find out the molar mass, give you the mass, give you the temperature, pressure, and volume. Right? So you see about the molar mass has a unit of gram or mole, which means if you want to really find out, do the calculation, just take the gram divided by the mole. Whatever the gram, you know how much gram of water here, right? You also know how much more of water here, so you have the same amount of material here, and you want to find out what is the molar mass, you take the gram divided by mole. Right? Now how can we find out more if you have the temperature, pressure, and volume? Ideal gas law, right? But ideal gas law, let's see, very quickly, I think sometimes I probably overemphasize, so I have this equation, ideal gas law, right? And what is the equation for mole? You want to find the mole, which is N. So N sure equals what? Right? Visualize what N sure equals. P weight over RT. Excellent. Okay? Awesome. So that's good. So I think most of you get it in your mind. Okay? So you just see, if you want to find N, you just use ideal gas law. You see that you will take that pressure times volume and divided by R and T. If you want to use this equation to find out N, and what is probably used for the pressure? What unit is probably used for the pressure? ATM. And volume? Very good. And then R, 1.08206. That's good. So you repeat and then you find you memorize. And temperature in what units? Kelvin. Right. So that's it. And that is pretty much the procedure. Okay? So if I have a problem and I give you like what is the mass of the sample, and what is the temperature, what is the pressure, what volume, you first You probably will take this, I mean, you probably, like what I did before, is use the mass divided by the volume in liter, get the density, then use that equation and find the molar mass. Okay? Otherwise, you do kind of like 2 steps. Okay? First, use this equation and find out N. And then when you have N, you take the gram which will give to you divided by what you find out, you get the molar mass. Alright, so that's 2-way. Okay? So 2-way to find the molar mass, and so that's the other way. Now, probably for this example, we will do like both ways. Okay? So the first way is molar mass. Okay? Molar mass equals to what? D times what? RT, and then divided by P. Okay? So that equation comes from D equals P times capital M divided by RT. You don't have to memorize all the equations, but if you memorize one equation, right? So if I want to use this equation to solve the problem, let me just see. You can do a very quick check. I want to use this equation to solve the problem. Do I have all the information? Do I have a D? Do I have a D given? Not directly. Do I have R? I have that. Do I have a T? Yes. Do I have a P? Yes. Right. So therefore, first you want to find out a D. So D sure equals mass divided by volume. Alright. And then you know this guy sure in what unit? Gram per L. Right? Now for this given problem, tell me what is the given mass in gram? 0.311 gram. Okay, I like to see that. That's very good. Okay. What is the volume for the same amount of gas? Tell you that amount of gram of gas is how much volume in liter. Is that given? Okay. So 0.225 liters. Right. So you quickly can think about what we have before, then just use that, and that's our first way. So then, once we finish this, we will talk about the second way, right? What you get is 1.38 gram per L. So this is our unit. So then, what do we do? Right? So if you want to use this equation, as I said before, your R is 0.08206. Temperature in what unit? Kelvin. Pressure from in what unit? ATM. And now let's make sure let's list out. Do we know the R? 0.08206. Do we know the temperature? Which will give you what? 55?
Plus 273.
Very good. You make sure in this temperature, so the temperature is all in kelvins, right? So what we have here then? 328 kelvins. Okay, good. So now let's identify the pressure. So right now the given pressure is what?
8860 divided by 760.
Millimeter mercury. And you know what unit is used for the pressure?
760.
That's sort of ATM. So you know you have 760 mmHg and 1 ATM. So that's to come out. Right. 886 divided by 760. You get 1.17. I just keep 3 6 figures. Alright, I think I'm almost ready, right? So we get a density here, 1.38. Alright. So what else do we have? What else do we need? 0.08206. What else we need? Temperature. And then the pressure is 1.17. Alright, so that's, I did not put all the units in. If you put all the units in, and you will count out all the units, you will get gram per mole. 1.38 times 0.08206 times 328 divided by 1.17. Right, so that I think it's 31.7 gram per mole. Am I right? Okay, any questions? Okay, so let me see this right now. Okay, I'm going to erase those. Okay? I'm going to keep that and do it here the second way. Okay. So what is our second way of finding water mass? Okay, so make sure you want to find the mole mass. You want to take the mass in gram and divide by the moles. Okay, now let's keep writing. Do we have the mass for this problem? We have a example of gas. We know how much. Do we know how much gram of lemon we have? Which is 0.311 gram. Another problem is, do we know the mole of this gas? No. So you want to think about find out the mole. What equation shall we use? Shall we use Avogadro's? Avogadro's, that means you need two like volume and two volume and two n. Do we have two volume? No. So we're going to use that PV equals n, r, and t. PV and t. Find out the mole. So from this equation you can see n will equals PV divided by r and t. Am I right? Okay. Okay, so if I use this equation, our pressure shall be what unit? If I use this equation, pressure shall be ATM, right? So we'll find the pressure here at ATM, the same pressure, just the same condition, just different way, right? Right, so we'll write 1.17 here. Okay. Do we have the volume for the gas chamber? What is our volume? 0.225. Okay, so what is our R? So 0.08206 is our R. What is our temperature in Kelvin? 328 Kelvin. So we have a 328. We don't have to use the unit. Alright. So this is about the second approach. So in this way, you first find out what is the mass and what is the mole. 1.17 times 0.225 divided by 0.08206 and 328. Okay, so you get 0.00978 moles. Okay. So what do we do next? We want to find the mole mass. We will take this mole, right, divide into that grams. So 0.00978, and so that is more. And obviously you take that on the 311 divided by 31.9 and has gram per mole. Right. So you have like many different ways to solve the problem. Okay. I think when you do the CRE, you also do like in this way. Just make sure you practice a different way. Okay. Any questions? Okay, so I use this example very similar as what we have here. Probably a little bit easier because I want to emphasize just those procedures, not some. In this one, you probably don't have to worry about the unit. I think all those units are ready. But that means that all those units is ready. Even though this question is not really to calculate the model mass, right? Do we need the model mass? Yeah, we can identify what gas we have if we know the model mass. Because each of those gas will have a model mass. Right? What do you find out? N2? Yeah, very good, very good. Which way do they use? They use that D equals PM over RT. Or that is easier way, right? Or you can use what I did here on the board, right? So either way. All right, very good, very good. Did you find out the answer is B? Answer is B. Which way you use? I like that. Yeah, that's good. So D times RT divided by T, right? Yeah. As long as you remember one way and just try to create all the information. Any questions? Very good. You're doing good, but you have to okay, I think most of you are doing that way. Okay? So I'm not going to spend time on that. Okay? You want me to do that one way? Okay, which way you want me to do it? So this way, or that D equal either way. If I do it, I will probably do this way because I usually have a better memory. I will not memorize like D equals P times M over IT. So if you don't want to spend too much time to memorize those, memorize some of those fundamentals. You know that the model mass will be like a gram over moles. So I do that, okay? So we say molar mass equals grams over moles. Then how do you memorize that? That kind of, you already know that many times. So you know like the molar mass has a unit of gram per mole. Okay? So then let's just list out, right? Grams for this program is 3.50 grams. Right? Now, to find out mole, to find out moles, to find out mole, in this chapter we use that little n, right? So I think there's two equations has little n in it so far. We have the Avogadro's and we have ideal, right? If you want to use Avogadro's, you have to know you have two sets. You have to have see like what is your two volume, what is your two n, right? So to find out the mole or n, right? We decide use PV equals n R and T. Right? So then why not the other one? Why not that V1 over N1 equals V2 over N2? This is the so-called Avogadro's law. Why not that? Not that because you don't have two volumes, you don't have like another n, right? Okay, so let me just simply cross this out. So not use that. Right? If you want to use this, your pressure should be 18 m. So this pressure should be 18 m. Right? Your volume should be what? Liter. Right? And your R should be what number? 0.082. That's 0.082. 82.06. What's the unit for usable temperature? Kelvin, right? All right, so let's think about we decide. So after a long way, we decide we use that equation, and then we also know what unit we use. Right? So that's why I said it right here, and that equation you can just plug everything in once you have the right unit, and you solve for n, or you can just get an equation for n, then plug everything in. Right? So I'm going to prefer this way. Right? So I will write n equals p times v divided by RT. Right? So then your pressure should be ATM. And that's good. This gives you the pressure 2.42 ATM. And your volume should be liter. That's also good. I said at the beginning of this CRE, so every unit is ready. Right? The R should be 0.08206. And your temperature should be in Kelvin, so that's very good. Right? I omitted that unit for R. If you take the unit for R, you will see all the units come out. You can save the n and then more. Right? All right, so let's try this calculation: 2.42 times 1.5 divided by 0.08206 and 355. 0.125 more. You probably did not use this way, right? So right now you have this one more. Alright, so then you just put it back into the equation you're starting from. And you have a 3.50 gram divided by 0.125 more, then underline the unit. Right? Do you follow me? You understand, right? 3.5 divided by 0.125. Okay, so you get 28. I get exactly 28. Right? And if I want to keep the right number of single figure, I will add in a 0, because if I only write 28, I only have 2 single figures. So if I add in a 0, now I have 3 single figures. Right? So you have this number. Right? Now this number, remember here you want to compare all those diatomic, right? And you do a calculation for this guy, the molar mass is 2.02. For this one, the molar mass is 28.02. For this one, the molar mass should be what? How about 70? Because it has 35.45, right? So 70.90 something. And O2 should be what? 32. And F2 about, something like, you have 19. Not 18. Right. So that's about molar mass. Right, I think the next section is about gas mixtures. It's very important. We are going to have some of those experiments, have some of those lab about gas mixtures. Right. So when gas are mixed together, their molecules behave independent of each other. So again, we're assuming we have the ideal gas. Okay. So all the gas in the mixture, make sure you read this carefully. All the gas in the mixture, not like before you have the mixture. So once you mix them together, all the gas in the mixture have the same volume. Because gas is not like a solid or liquids. Liquid, they cannot go to the top of the container. So therefore, they will go to every corner, every part of the container, and all the gas will have the volume of the container. right? So each gas fill completely the container, so therefore each gas volume equals volume of container. Because they are all at the same container, when you mix them, before you mix them, you might have a hot gas and cold gas, so obviously you have different temperatures. But once you mix them, afterwards they will become equilibrium. Okay? So the cold gas will cool down the hot gas will warm up the cold gas. So therefore, you have the gas mixture, all of them will have the same temperature. So I talked with one of you like before the class, and you also know like they have those different components have different mass, and at the same temperature, which means their kinetic energy are the same. Okay? Because kinetic energy are the same, and they have a different mass, so therefore they might have a different. If they have a different mass, for sure they will have a different speed, a different velocity, and they have all the same mass. So don't think about you have the same temperature, they all have the same speed. What they have the same is in this, you know that they have the same volume, same temperature, same KE. Same KE that means they have the same speed, because you know KE is the kinetic energy, right? Right. So we don't have that in this section, but it's probably next section we'll see that. So therefore, let me have that. So they have the same KE. So KE, let me write that KE equals half and m times v squared. Okay? You know that's the common formula, right? KE is the so-called kinetic energy, right? That equals 1/2 of the mass times velocity of the velocity square. So when you square, you don't have those direction. Just have the quantity. Right. You can see what I said. If you have the same KE, this is the same. And you can see oxygen gas, it has different mass than CO2, and CO2 have different mass than iron and N2. So this number is different, right? And you want to get the same number here, this number must be different. Does that make sense? Right? So you want to have like some of those numbers multiplied together have the same number. And if some of those gas has a heavier mass, have a larger N, and you don't need a larger weight to get the same number. Right? So for example, if you have that KE is 20. Now how you get 20? I just some of those random numbers. I say that's 20 for KE. Right? And the 20 KE will equals 1/2 times m, and then v squared. Okay? Now, if you have that, let's say you have that H2 molecular, right? And this m will be 2, right? So you have 2 times that, and v squared, and equals 20. And if you have the same room temperature and another gas in it, let's say that is N2, and you have 1/2 and 28 times V2. And obviously, you have the same KE, so therefore 20. And the formula is the same, so 1/2 times mass V squared, and you find out. So for this one, this V will be much higher because you have a small number, you have 2 divided by 2, you get 1. And you want to get a 20, your V will be larger. Now here you have 28 divided by 2, you get 14. And you already have 14, you want to get 20, now 14 probably times 1.5 or 1 something, you get 20, right? Does that make sense? Why you still, it seems like you are confused? Alright, so I think you're okay, so you just know that you see out. Alright, so now you read that. So now if we still study those ideal gas, okay? Because we see like many times the ideal gas has no difference. I mean, they have a different mass, different speed, but in some sense they don't matter, right? So therefore, what I want to emphasize is this: you can consider them as one gas. So for example, this air has O2, N2, R1, CO2 in it. You can measure, calculate how much more of all those gases together. And then once you get that, so in some of those approximations, that is the same as, for example, if you have this air here, you figure out like 20 moles, and then you can take these 20 moles to the calculation, like for the pressure, for the temperature, for this 20 moles of air, same as you take 20 moles of H2. That's only for those temperature and pressures. So even though the air is a mixture, we can measure the pressure, volume, and temperature of air as if it was one pure substance. That's what I try to emphasize. Okay? So if you measure pressure with P, volume with V, temperature with T, okay? So once you measure that, and you can calculate what is N. N will equals P times V divided by T. So even though your air is a mixture, you use the same formula to do the calculation. So let's say in one experiment you measure the air. You use this formula to calculate how much more you have. Now in another experiment, you measure like the pure nitrogen gas. And you also measure these few numbers. You measure what is the pressure, what is the volume, what is the temperature. If you get the same number in both experiments, so one experiment is air with mixture, and the other experiment is a pure N2 gas. Now what this few sentences here tell you is about this. If you measure the air, you get the T, you get the P, you get the volume. If you measure this pure N2, you also get the T and V. Now let's make another assumption. If in both experiments you get the same temperature, same pressure, same volume, same temperature for the pure, same pressure, same volume. Because we're assuming those gas, air is the ideal gas, N2 is the ideal gas. So therefore, if you want to find out how much more do you have, you end up with this equation. If you plug into this equation with the same temperature, same pressure, same weight, you will get the same N. So even though the same N, really, they do not tell you really like in details, you might have 20 more of N2, or you have 20 more of those mixture. And in the mixture, how much more of N2 do you have? How much more of O2 do you have? How much more of other gas do you have? So sometimes you don't care, just say, I have 20 more of gas. But sometimes you care, you will see how much more of those each component you have. And so then you want to figure out how much more of each component I have, you need more information. Right? So altogether, let's see the air, we have the 1 ATM, and then we know in the air we have N2, O2, CO2, argon, water vapors, and we have altogether 1 ATM. So we have a total pressure. Right? We have a total pressure. This total pressure is sum, is addition altogether of those pressure from each one component. So then the pressure from each component, we call them a special name. We call them the partial pressure. Even though in the mixture, when you have that volume and temperature are the same, when you mix them, but you still consider each component, like the N2 gas, O2 gas, they will have different pressure. They will contribute to different pressure because the gas here, the air, like striking on the surface. So which of that strike on that? If you collecting all those collision from N2, so those pressure produced is called the pressure of N2. Then all the collision come from O2, where we produce the pressure from O2. Even though the N2 like moving a little faster, the O2 a little moving a little slower, kinetic energy are the same. Then what makes the difference is also how much N2 you have in the mixture, how much O2 you have in the mixture. And obviously the total pressure of N2 depends on how much N2 collide, how much O2 collide. Right. So this was noticed by like the Dalton. So Dalton summarized, when you have those gas mixtures, you might have different amounts, different more of those components, like in the air, N2 and O2. So you have like some of those percentage, either by mass or by more of N2 and O2. And so those information convert into their partial pressures. And what you find out, if you know like those more of each component, if you know the more of N2 or the O2, and right, so those number more is N. And let's see the air again. Right? So air has N2 and has O2. These two measure components. Right? So if you somehow measure out what is the more of N2, you just use this notation. You see, little n, subscript N2, that means more of N2. Right? So then you also know their volume and their temperatures. Right? But for each one gas, for N2, you only have one set. For N2, you have one more, one volume, one temperature. Right? So therefore, you can use this equation to figure out what is the pressure for those N2. And in the air, you also have O2. So if you somehow measure out what is the more of O2, so what is the more of O2? And I also tell you the O2 is also in the mixture. So if they are in the mixture, they will have the same volume, same temperature. Right? So therefore, you can use the same equation and find out what is the pressure for from that amount of O2. Right? Use the same equation, so PV equals nRT. Even though in both this gas, I did not write clearly what will be the equation for P, but you know you can solve this equation by divide the way out, get the pressure. Right? So in general, when you have a gas mixture, you have a different N. Right? You have a different N for those components. So if you want to finish this question, you just put here this N from N. So this little notation you can replace by that N, N2. And this one you can replace by N and O2. Okay? Right? So in general, you have a gas mixture, you have different amounts, different number of more for those components. Right? So even though they have like those different like amount of moles, but they still have the same temperature, same volume. Right? But when you put it into this equation, usually when one is different, so they'll make the pressure different. Right? So if you also can put this pressure here, is our pressure N2. And here is the pressure of O2. I think the last couple of steps I lost you. right? So I think later on you are recovered. Those are just tell you have those partial pressure. Right? So the partial pressure adding together is the total pressure. So this is what, as I said, was noticed by the Dalton. Right? So this is what the Dalton's law of partial pressure. The reason is each gas behave independently. So for example, so we have the air, right? And we have these few components. Don't confuse by this volume percent. Right? So even though I tell you when you have an air mixture, so all of them have the same volume. So then, where does this percent of volume come from? Obviously, here you have different percentage. What that means is, before you, let's say you have this room of air, before you make up this mixture, let's say this room of air is 20,000 liters, right? So in this 20,000 liters, and you have some of those, most of them is N2, and most of them O2. So you mix them together, they all become like their volume for N2 and O2 all become like 20,000 liters. But before you mix them, you want to make up this total 20,000 liters, and how much liter of N2 do you need? Same pressure, same temperature. You just take like 20,000 liters times 78%. So that's what we mean by the volume percent. Right. So then the Dalton's partial pressure law you can really prove. Okay? You see, prove that it's true. What that tell you is total pressure equals the partial pressure adding together. Okay? And so what that means like this, okay? You can do a very quick calculation. Okay? Let's say you have two gas. Okay? So gas A plus gas B, and give you a mixture. Right? So let's see how much more we have. So for gas A, we'll see we have that amount more of gas A. Okay? For gas B, we'll see we have that amount of more of gas B. Okay? Now in the mixture, how many total more of gas do you have? Probably Na plus what? Nb. Alright, now you follow the line. Let's say they are in a mixture. We have a mixture, so they will have the same T and the same weight. That's the mixture. Even though in the last slide we have 78% by volume of N2 in the air, but that means before they mix. So when they mix, they have the same temperature, same volume. Alright? So now what do we call them? We just call them temperature and volume. So this is for this gas A. Right? Now they have the same temperature and the same volume for gas B, so therefore I will just put that in the parentheses for the condition of gas B. Now what is the temperature and volume for the gas mixture? The same. Right? Okay. Now let's find the pressure for these three. Let's find the pressure for gas A, find the pressure for gas B, and find the pressure for the mixture for everything together. Now tell me what equation shall we use? Shall we use the Boyle's law, the Charles law, the Avogadro's law, or the ideal gas law? Well, ideal, Brad.
You're treating it as one gas.
Depending on how many we know. How many N's we have for each gas? one N, one T, and one V. We have two N, but that's for different gas. For each one gas, you only have one condition. Okay? Alright, very good. So you are going to use to find P, use PV equals N, R, and T. I will say R, P equals N, R, T divided by V. You agree? Now, this equation you can use for all these three gases. The first gas is called gas A. The second gas is called gas B. And then gas A plus gas B together called gas mixture. You consider that your gas 3. Right? So let's find out what will the pressure for gas A. We will call that PA. Right? So we all use the same equation for all the three different gases. In this equation. In this equation again, what is the same, what is the difference? For these three gases, in this equation, what are the different, what are the same?
Molar is different.
More is different. Here you can see that Na and B, very good. What else is different? Now, probably want to see what is the same. Temperature is the same. The temperature. What else is the same? Volume. Okay? Now, because this is the same, this is the same, so everything here is the same, but as long as you have that difference, even though R, T, V are the same, so therefore, what you can see about the pressure? Different. Okay? Yeah. Right. So pressure will be different in general, in case you kind of like coincidentally have all the same numbers. Alright, so now what is the pressure for the gas A? Very good. Na times what? R. Very good. Right. You don't have to say TA or VA because they have the same what? Same temperature and same volume. Right. Now let's do another calculation for the pressure of gas B. And we will call that PV. So therefore PV will equals, PV will equals NB RT divided by weight. Right? Now what we will call that this guy? We'll call that P, we'll call that total. Right? So we'll call that total. Right? But that's really science in adding together. Right? So if we call that mixture of gas is P total, so therefore P total, that will equal what? Very good. So these are our total mole, right? Then similar, multiply this by what? RT. Okay, keep going. The other way. You probably already see the relation, right? So this is our pressure of come from the gas A. This pressure comes from the gas B, and that's the total pressure. What is the relation between this total and this P and PV? Do you see that? What is the relation between this P total? You probably can see that, or you probably just see that just one step. So our P total is Na plus Nb times RT divided by weight. Right? Our PB and PV. So our PB will equals Nb times RT divided by weight, and our PA will be equals Na divided by weight. Do you see the relation between these three equations? If you take this equation plus this, right? So if this plus this, so in both of these, what do you have are the same? RT over weight, right? RT over weight. Remember what we learned in algebra? we have two terms, and both of them have the RT or weight. And what we can do is, so we still call that ND first, and ND second, so we can just write something like this. Do you agree? And then you compare this with this. This and this, that's it. So that is use ideal gas law to prove that Dalton's partial pressure law is right. Yes, that's so easy. If you study liberally, you just spend a little time. Very good. All right. So then we are going to learn how to use this idea. So what we get is the Dalton's partial pressure law, which means, so if I rewrite, so I will just get this Dalton's partial pressure law is so-called P total equals PA, right, plus PV, and plus so on, if you have more components. Right. So then once you know this, and you still have that equation like that PV equals nRT, that equation, right? You still have also Boyle's law, Charles' law, Avogadro's law, but depending on what kind of situation you have, for most of the problem, like I think from now on, you probably use this ideal gas equation, right? So now you analyze the problem, you read the problem, let's see, what you want to find out is mass of argon. Okay? You want to find out a gram. So you want to find out grams. So I think in chemistry, one important conversion, as I emphasized in chapter 1, is converting between gram to what? To moles. So sometimes if I ask you the mole, you can think about the right way about a gram. Okay? If I ask you the gram, think about the right way about the mole. Okay? So if you want to get the grams, you have to think about getting the mole. Right? For the gas, how you get the mole for the gas? Right? So I think about which equation has the mole in it. The Avogadro's law has more in it. Right? Avogadro's that V1 over N1 equals V2 over N2, that's Avogadro. Right? And you also have that PV equals nRT. That equation has N in it. So again, just like boil down to like what equation you should use, right? Right. So you are going to use this ideal gas equation, okay, to find out this guy. Because once you have the N, you have the mole. Once you have the mole, if you know the identity of the problem, if you know your gas is argon, your gas is helium, you can multiply by the molar mass, get the gram right away. Right? So that's how you usually you think about the problem, what you need to find out, and what you need to find out intermediately, not really solve the problem right away. Right? So we decide we have to find out more. Right? So we decided we had to use that PV equal to nRT. And obviously to use that equation, you want to find out the N, what else you have to know? Okay? You have to know the pressure. You have to know the volume. You have to know the temperature. Right? So then depend on the problem. If the problem gives you the pure gas, so you will have a pure gas pressure, the pure gas volume, and pure gas temperature. Right? But if the problem gives you the mixture, and then you remember, once you mix all the gas together, so all the gas will have, all the gas components will have the same volume and same temperature. Right? So now, what could be the difference to make them have a different number of mole is the partial pressure. Alright, so after you analyze all those problems, you want to find out N, you want to use this equation, you need the partial pressure. Okay? And you need to use the volume for the gas mixture because once you mix, all that will have the same volume. Okay? You need to use the temperature for the gas mixture. Alright, so we want to find out N. N will equals PV divided by R and T. And now let's just do the first one first. Right? How can we find out the pressure? Okay, now make our thinking a little bit clear. Let's think about, for this particular problem, what gas N, what's the mole for what gas we want to find out. Gas for what, the mass for what gas. So therefore it will be mole for what gas? Argon. Okay? So therefore we want to find out the mole of argon. Okay? Now argon is, do we have a pure argon? We have argon in a mixture. We have a mixture. Okay? Now in a mixture, what do we have are the same in this equation? In a gas mixture, these four letters, what are the same? What is the difference? When you have a gas mixture like an argon in it, you want to find this mole of argon. That will depend on the pressure, depend on the volume, depend on R, depend on T. So in that equation, what are the same? What is the difference?
Temperature is the same.
Very good. The temperature is the same. The volume is the same. The R is the same. What the difference is pressure. Okay? If they are the same, you don't have to make a notation. If there are difference, so you have to make a notation. Well, of course, this is the PR. I mean PR, PER. Right? We don't have to make a new variable called that V argon because we all have the same volume. We don't have to use a different letter for the R because we all have the same R. We don't have to use a different temperature because we all have the same temperature. Alright, so now let's try to identify what is our P argon. Okay, probably you are saying, oh, I want to find a P argon, go back to use V and N, R and T. You don't go in a circle like that, right? You're going forward, right? You want to find out, you want to find this P argon, right? Because you need this going forward to find out N. Right? So what other information you can use to find this partial pressure of argon by itself? Very good. So here we go. So you have the Dalton partial pressure law, right? So this will equals the P total minus what, depending on how much component we have, right? What component we have? We have a helium. What else do we have? We have neon. Right? Extremely for the body like this. So that means if you want to find out the partial pressure of argon, you will take the total pressure minus the partial pressure of helium, if you know that, right? Then minus the partial pressure of what? Of neon, if you know that. But in this step, because you are doing subtraction and addition, right? You can do it in any unit as long as we have the same unit. Right? But once you find out the partial pressure of argon, you want to put it into this equation, and you have to think about what unit should be used. Right? Right. So let's first find out what is the partial pressure of argon. Do we know the total pressure? Okay. Do we know the partial pressure of helium? 341. Do we know the partial pressure of neon? All those are in what unit right now? Is mmHg. Right? So as I said, for this step, you can convert all of them into ADM and do the subtraction. Right? Or I can do the subtraction first, and then we will convert. So 662 minus 341 minus 112. Right? you get 209 millimeter mercury. Right? So we kind of get one number ready, right? So we want to find out this N. We need all those four numbers, four letters. Right? So we find out this P argon is this number. Right? Shall we use this unit right away or shall we convert? We have to convert.
I was gonna ask you why didn't you convert before we?
Yeah, you can do that. You can convert. I think there are probably little more calculations, right? You can convert this into ATM, and this into ATM, and this also into ATM. So you need to do 3 conversions. Or you can just subtract and get 1, and just do 1 conversions. Right. So if you have like a lot of calculation, you are thinking about save some steps as many as possible. Right. So what you do, you will take this 760 and millimeter mercury. Understand? So this mmHg come out, which means you take 209 divided by 760. Very good, Brock. I cannot see your name. 0.275 ATM. So these are the 2 numbers, right? So now you get the partial pressure, which is in ATM of this argon gas. So you're almost there, right? And you want to find out N, then make sure you identify the volume and what number you use for R and what temperature you use for the argon. Right? Right? So now let's write here. Okay, so we call that N argon or equals P argon, right? Divided by times V divided by R and P. So let's continue to write. We just find out 0.275 and that is ATM. Right? Now what should we use for the volume? Do we have the volume? What volume do we have? 1.00 liter. Should we use that right away or should we figure out what is the volume for the argon? Why just the same? Because once you mix, so all the gas can go to like all different places. What R should we use? So again, when you calculate those like the moles and pressures and volume meters, so that is the common number you use for R, right? So the other is temperature. What temperature we have for this? For this particular one gas, what number should we use? Can we use 298? Just tell us like the temperature for the mixture. Yeah. So when we have the mixture, that means all the gas have the same temperature. Right? So we have 298. Right. So that's a very typical problem. So you just so you take that and times 1 divided by 0.08206 and then divided by 298. Right, you get 0.0112, which has unit mole, right? And obviously we will have the identity of the gas, which is argon. Right? The question asks you what mass in the mixture. So once you have this amount of mole, and then you have for every 1 mole of argon, so then let's say the argon is 39.95, right? 39.95 gram. Right, you get 0.449 grams. That's not really new, so we pretty much continue with that ideal gas law, PV equals NIT. What is really new here is we find out what is the partial pressure of one component. Okay? And There's some other details. You have to be able to identify the same volume and same temperature for all those different gas components. Okay, pretty good. I see you getting like a little more like understand and do it easier. Alright, so that's pretty much what we saw before. Similar idea, there's a similar problem as the example. Right? So you have a gas mixture of H2 and N2. So the total pressure remember the answer. What do you find out? E 1.99. How do you solve the problem?
I subtracted the total pressure from the pressure of H2, and converted torr into ATM, and then plugged the ATM into the ideal cathode. And then
From there you find out
we find out the moles versus the molar mass.
when you can do that, okay? Yeah, that's good. That's why you get like a 30 out of 30, right? On the exam line. Now, I put the exam line, your score on the campers, on the iCampers. All right. Any question you want me to write down the procedure? Or you want to write down the procedure? Okay. Write the procedure here. How you get that?
Okay.
You can explain like step by step when you do it.
Okay, so it gave you the total pressure, and using Dalton's theory, you can use the total pressure minus the part that you're given from hydrogen to get the part from N2. And once you have that N2 partial pressure, you can convert the torr into atmospheric pressure, which gives you this number here. Once you have that, you can plug it into the ideal gas law equation. And what you're looking for is the number of moles. So all the units cancel out, and all you're left with is the moles of N2. But they're asking for grams, so you take the number of moles and you use the molar mass of nitrogen, and you get your answer.
Any questions? Why you use like the volume for the gas mixture for the volume of that gas?
Why do I use
Of
this
the
up here?
gas? Yeah, that's a pressure. Yeah, why you do that?
Because Dalton's theory says that the total
Total pressure.
pressure is equal to the sum of the parts.
Very good. And you solve pressure, right?
Yeah. What were you asking?
What? Yeah, that's a problem. What volume do you use?
The volume I
Mhm.
used was volume of nitrogen.
Yeah, what volume you use for the nitrogen gas? 2.2
Oh.
liters. Yeah.
Oh, 2 liters, yeah.
Why use 2 liters? That's the volume used for the mixture.
Well, the volume of the mixture is
The same as
the
for
same as the volume of the
component.
part, because
Yeah.
gas takes up the entire container.
Very good. Yeah. Why use the temperature? What's the temperature you use for the mixture?
298.
Why use the temperature for the mixture for the N2 gas?
Because when two gases mix together, once they reach equilibrium, they reach the same temperature.
Very good. Okay, so any questions? And you probably ask, why you starting with find out N? Why you start with find out N?
Just finding out the number of moles,
Yeah.
because once you find out the number of moles, you can just do a simple molar mass conversion to find the grams.
All those choice about the gram. What's the question?
Is torr is converted to like, I
Yeah,
don't
yeah,
need
yeah,
to change
yeah.
that.
So the
Except
core.
the-
Yeah.
Any other questions? Yeah, that's good. We do not use torr too much. So the torr is the same as millimeter Hg. Understand? That is okay. So that's fractions of the total pressures that. So we're going to learn those more fractions, right? Because that will give you another way to find out the total pressures. If you know the total pressures, if you can somehow find out the sort of more fractions. Okay? So what that tell you, like also like you how the scientists, the audience, you find out. Okay? So fraction of the total pressure is the same as the fraction of the mole. What that means, if you take the pressure, for example, in last problem, okay, of N2, divide by the total pressure, okay, and that therefore equals the sort of the fraction of the pressure of N2. And that will equals the mole fraction of N2. Mole fraction of N2 will equals mole of N2 divided by the total mole. Okay? So you speak it in like a mathematical language. So this paragraph just tell you PA divided by P total equals NA divided by N total. You're already familiar with those notation. Okay? So P total means the total pressure, and N total means the total mole. Right? So then you will give that a special name for that. You will get that special name for that NA over n total. And A over n total, you will call that more fraction of A. And you will call that XA. Okay? So once you have that, and you can replace this by XA, right? Because NA over N total equals XA. So you put XA here. Understand? And so, because from this equation, we know this guy has a name. This is called XA, the more fraction of A. Okay? So then, how you get this one from that one? Probably the simplest question you can ask it for yourself. If you have PA over P total equals XA, and how you get this PA equal to that? How you get that? How you get this? Multiply by the P total. So P total comes out on there, right? So therefore, you can do the subtraction like what Brad did here. You have the total pressure subtracting by the total pressure of one gas, get the total pressure of another gas. Okay? Or you have some other information, somehow you find out the mole fraction of one gas, and you just multiply the mole fraction of one gas by the total pressure. You get the total pressure of this gas. Right? So even though sometimes, probably do that like strategy. Right? So strategy will have that another lab. So you just you can prepare some very useful chemicals called argon from some of those argon from these aluminum chemicals. So read the lab menu.
Really? So lucky to get that. Oh, that's so rough, dude.
Why were you here?
I got a question there. So you were just staying in front of the room. You didn't know anything. You could get your own time.
Yeah, the super legal. Yeah, I'll take that. That's it, I guess, right. Signal down on 515.
Okay.
There you go.
Okay, that was, yeah. I just didn't realize if it was this one, or I know that before I've seen that, for me, I was gonna take it in like, yeah.
I was just saying something
I'll
that,
be
hey,
like,
see
what?
what,
I was just pissed off.
oh, I was just at one of them. Time to leave.
What's wrong with you?
I fell up a staircase.
Is it cold?